This is the derivation for inclined plane and banked curve. They're really related to each other, so I'm doing both derivations at once for one video. I figure there's two ways to lecture over something. One way is just read everything off like you're reading it out of a book. A book just states the facts. So if somebody's reading the facts from a book, they can stop, reread the same statements over and over, look at the same diagram over and over, and that would give them time to really be able to process everything. But a book just states the facts and goes really quick. If a teacher is lecturing about something though, a teacher will tend to go slow and give people time to process things, and a teacher will tend to repeat the same things over and over at times to really help give the students a chance to process everything and understand it. I'm going to take the book approach here and just state the facts. So pause the video and rewind it as many times as you want to get each fact or to understand each fact. There's 12 steps here. Every step is actually really easy, just a baby step. But most of these steps are going to build on top of previous steps. So learn each step and understand it and remember it, because I'll be covering those same steps on future pages. The nice thing about organizing everything into little baby steps is if somebody doesn't get something or they don't understand something, they can say specifically which step it is they don't understand. For example, they could say, I have a problem with step number 8-11.73, subsection A, paragraph 4, and the fourth letter in the third word of the 12th sentence, or something along those lines. But this lecture doesn't get into that kind of detail, fortunately. I figure with 12 main steps here, if I did 1 minute for each step, that'd be 12 minutes. Hopefully I don't go to 2 minutes for each step, because that would be a 24-minute video and that'd be a little bit long. So process every baby step. They're easy baby steps to process. And then remember it and be ready to use that step for the next page. First step here, step number 1, we have our basic trig diagram. There's your angle theta. Cosine of theta is adjacent over hypotenuse. Sine of theta is opposite over hypotenuse. As you increase your theta or increase your angle, that will increase the sine and that will decrease cosine. As you decrease the angle, that will decrease your sine and increase the cosine of theta. Every arrow is a vector, and that vector means force. Increase your vector means you increase your force, so we have a long arrow. Decrease your vector means to decrease your force, and you'll have a short vector. For example, the vectors on this diagram right here, we have a long cosine vector, so we'll have a large force in the x direction. We have a small sine vector, so we'll have a small force in the y direction. Next page. This is simple, just pull a block across the floor. F sub p is the force of pulling. That force of pulling will be resisted by F sub mu, which is the frictional force. F sub d is the downward force. That equals mg, mass times acceleration from gravity. That is the fuel that powers all the reactions here. Everything will start with mg. In other words, mg is the main vector. All the other vectors will be built off of mg, which is your downward force. Centrifugal force will be the only exception. I'll cover that at the end. Centrifugal force does not come from mg, but everything else does. You have your downward force pushing down, mass times acceleration from gravity. There's going to be a reactionary force called the normal force, and that pushes up. So your normal force has to equal mg, otherwise this block will fall through the table and go to the center of the earth. So it's the same thing, but it has different names. Your downward force is the same thing as mg, which is the same thing as your normal force. And right here I just said it's the same thing as downward force. I'm going to call this a right angle rule right here. Take any of these terms because they all mean the same thing. mg, downward force, normal force. Put a mu next to it and you go up to a right angle, and that gives you your frictional force. So downward force times mu, normal force times mu, mg times mu. These are all your frictional forces, or it's actually just one force with several names. Those frictional forces come from the normal force. The normal force comes from mg, which is your downward force. So downward force powers everything. And remember that right angle rule, I'll use it later. Your normal force right here is what measures the weight on a scale. So if you put a scale right there, then the normal force would tell you how much that block weighs. Here's how you can get your frictional force. We just take our downward force times mu equals your force of pulling. But let's set that pulling force equal to our frictional force. So what we have here is just downward force times mu equals the force of pulling. That means we can divide force of pulling by downward force. We get mu. Downward force is the same thing as mg. If you had a tension scale on your rope, so it would measure how much force you're pulling on your rope, you can measure your own μ's at home. You just take your force of pulling, divide that by your downward force, or m times g, mass times acceleration from gravity. That'll tell you what mu is. So mg is just the weight of something here on Earth, and if you have to pull on something really hard and it doesn't weigh very much, that's going to give you a large number divided by a small number, which will give you a large mu, or large coefficient of friction. As a side note, coefficient of friction comes as either static or dynamic, also called kinetic. If something's sitting still, it's harder to get it moving because there's a static friction. Once it's moving, it's easier to pull because it's just kinetic friction, which is smaller than your static friction. Next page. We have a block sliding down an inclined plane. The angle of the inclined plane is alpha. mg pulls everything down. It powers everything in this video. Your normal force has to push up to resist that. Again, normal force is just reactionary. These forces have to balance. Otherwise, mg, or the downward force, will just push everything down to the center of the Earth. Normal force is strictly reactionary, which means you have to have mg in order to have a normal force. If you remove the mg, then you're not going to have a force thrust this block up into the air. I just said here as a side note, mg is what gives you your normal force. And the normal force is what gives you mu, so mu comes from mg. mg also gives you your forward force. This block wants to slide down right here with a forward force, and that comes from mg. Imagine a scale underneath this block right here. If this angle alpha is all the way down to horizontal, you'll have maximum weight on that scale. If you make this angle alpha really steep, and you have a scale underneath that block, there will not be very much weight on that scale at all because the block will just want to slide down. So if, say, you screwed a metal plate to this inclined plane right here, or this ramp, and you made this ramp really steep, most of the force of this block would be sitting on that metal plate, and it would not register as a normal force if you put a scale underneath it. This page is primarily to verify our angles or prove our angles. Alpha plus beta plus 90 has to equal 180 degrees. I did a separate video proving the interior angles of a triangle, so you can see it if you want to. It's super easy and kind of fun. That means that alpha plus beta will equal 90, and then that means that 90 minus beta will equal alpha. The normal force comes up perpendicular to the plane. Therefore, if you go take this ramp right here, this plane, go up, turn 90 degrees, that gives you the normal force. Normal force always has to be 90 degrees or at a right angle to your plane. So beta plus some angle has to equal 90 degrees. Therefore, 90 minus beta has to equal alpha. We just said so right there. A couple more angle proofs. This will be a parallel angle theorem. I think it's called something like that. If you have a diagonal vector right here, or line segment, and you have a line coming up here, that'll be angle alpha. Keep this line parallel to this line, and both of these angles will be alpha because it's just like moving your pin up and down that line. Next will be some sort of opposite angle theorem. I think that's what that's called. I don't know. We have a rectangle. Each long side is equal to the other long side. The short sides are equal also. Angle alpha sits between the long side and hypotenuse. And since this long side is the same as that long side, then this has to be angle alpha because it sits between the long side and hypotenuse. So it's just the opposite angles have to be the same. Remember these because I'll use them later. This is the same inclined plane right here, just a few extra lines. There's a forward force on this box that wants to, there's a force on this box wanting to slide it down. If you put a scale right here, you would measure that forward force. Or I should say net forward force, because there could be a frictional force holding it back. Normal force comes up perpendicular to your plane. mg comes straight down. Now we have to decide which one of these lines do we want to be our hypotenuse. Do we want mg or normal to be the hypotenuse? Always make your hypotenuse 100%. The hypotenuse will be the standard to which everything is compared in this video. In other words, the hypotenuse will just be 1. So cosine of 0 equals 1, for example. That means since mg has to be 100%, it cannot change because gravity is always the same. The mass of the object is always the same. That means it's the normal force that has to change, and that normal force will change. Now that we've proven that this theta will equal that theta, or this angle equals that angle, now you can imagine making this ramp really steep. This angle will get really large. That angle will get really large. And as I said on the first page, if you increase your angle, you decrease your cosine. So that means your normal force will shrink down this vector, which is this arrow. That means this arrow here will get smaller and smaller, and that corresponds to less and less force. Notice here, if you're traveling down the road and you make two 90-degree right turns, you'll be heading back parallel from whence you started. So let's go up this way, turn 90 degrees to go down the normal vector, turn 90 degrees again, and that's how we know that this line right here, this sine of theta, will be parallel to that line right there, to your ramp. When I first learned this, I had trouble figuring out which one to make my hypotenuse. I tended to want to make the mg, I tended to want to make the normal force the hypotenuse, and then I would have a horizontal line going across, and that's just not right. So sine of theta equals your opposite, but since this is a rectangle, that means this is theta also. That means this will now give us a forward force. I almost got a little ahead of myself, sorry. I want to do normal force first. So what is the length of this normal force vector? So it'll be the cosine of theta equals adjacent over hyp. Cos theta equals normal over mg. Right there, that means mg cos theta equals your normal force. We'll use that later because remember, friction comes from the normal force. The larger the normal force is, the more friction you'll have. But for now, let's take the sine of theta will equal opposite, which will be the forward force over hypotenuse, which is mg. Sine theta is forward force over mg. Mg sine of theta equals forward force. Notice how we can break this up though. We can take g sine theta, that will equal the acceleration. Mass times acceleration equals force, therefore g sine of theta will equal your acceleration. So if you want to know how fast this thing will accelerate down compared to gravity, you could use that equation right there. But we're going to use mg sine of theta to get the full force. As a tangent, don't be fooled by this decreased acceleration of g sine of theta. If you have a frictionless ramp and you slide down it or slide a box down it and say that acceleration is half the acceleration of gravity, that does not mean this box will hit the bottom with half the force. This box right here may have only half the acceleration, but it's accelerating over a longer distance, so when it hits the end here, it'll have the full velocity or the full force. I did a separate video explaining that, so if somebody's falling with, say, pole vaulting or going down a slide like this, I went through the math and the proof to show that this box would hit the bottom here with the same force as if you just dropped it. But that's not an issue for most slides because most slides will round out at the bottom, so it can slow down gradually. And the less steep this is, then the more friction you'll have to slow it down, so it'll fall slower. But that was a tangent. So now we've solved the forward box right here, this forward box right here, this rectangle or whatever we use to tell how much forward force we have. On a future page, I'm going to show the backward box. So it'll be a box that goes behind this, and that'll tell you your backward force, which will be your frictional force. I was a little bit redundant here as I made these notes real quick. mg, or the weight, powers everything. Mg gives you your forward force, as I just showed, which is mg sine theta. This also gives you your normal force. Sorry, I guess I should say mg gives you your normal force, and that normal force gives you your frictional force, which is the backward force that pulls things backwards from friction. Friction is a reactionary force. So friction will not just pull something backwards. Friction only happens when you're trying to pull something forward. Next page. I guess that previous page wasn't too redundant because I guess it was a good idea to cover the backward force again. Here's our box right here. It wants to slide down. This is our forward force being opposed by the backward force, which is friction. And again, backward force is just reactionary. Notice what we have here are two right angles sitting on top of each other. Here's one right angle. I'll show with my pen right here. So you got your mg, you got your right angle rule. Mg times mu gives you mg mu at a right angle. That's why I called it a right angle rule. I just make this stuff up. But we have another right angle sitting on top of that. The normal force coming up here, perpendicular, and then that goes up the ramp right here. And thus, maybe you can see this angle opens up right here at theta. Then that means this angle will open up theta as well, because we just have this line right here swings out, which means this line right here swings up, if that makes sense. So we could prove that this is theta from two different ways. One is by having the same, coming off of the same right angle. The other is it's a parallel line from the main ramp. So that's how we know that this is theta and that's theta. Now I'm going to look at the backward force, which is F sub B. How do I know if I should make the ramp the hypotenuse or should I make the horizontal line the hypotenuse? I've already established the right angle rule that mg times mu means you go up to a right angle, and then you get mg mu, so that right there has to be the hypotenuse, which means it's not going to have any sines or cosines in front of it. So mg times mu just goes to mg mu. But another way to look at this is a horizontal surface gives you maximum friction. Therefore, I have to make the horizontal surface the maximum value, so it has to be the hypotenuse. So I can put my right angle next to the ramp, or I can put it next to the horizontal line. If I put my right angle at the horizontal line, I'll have a vertical line that comes up, but instead I'll put my right angle here coming off the ramp. So then that way it'll come down at an angle and make mg mu the hypotenuse. You could also say mg mu cos 0 degrees because that's at 0 degrees. So cos 0 degrees equals 100%. As I warned at the beginning of this video, most of what I say will continue to come back and haunt us on future pages. So in this case, as we increase this ramp here and make it steeper, we'll increase this angle, which means we increase this angle, which means we increase that angle. And as I said at the beginning, when you increase your angle, you decrease your cosine. So normal force is the cosine of this angle, and your backward force is also the cosine of the same angle. So as this ramp gets steeper and steeper, you will decrease your normal force, but your frictional force comes from your normal force, which means the cosine of both of these angles will decrease the same amount. So if this normal force decreases by half, then that means your frictional force will decrease by half. That means that the lengths of both of these arrows will decrease by half because these arrows represent force vectors. And I just said here, hypotenuse equals 100% of the force. So we made that horizontal line the hypotenuse. Let's find out our backward force right here. So that's going to be cos theta equals adjacent over hyp, which is your backward force over mg mu. And we get this right here. Cos theta equals backward force over mg mu cos theta equals your backward force. Next page. We're on step 9 out of 12. Here's our ramp, here's our block. Wants to slide forward with a force of mg sine theta being pulled back by friction. The backward force, mg mu cos theta. We can take our net force if we want to, which means if we hold a scale up here on this block, keeping it from sliding down, how much weight would register on that scale or how much force. Let's just take our forward force minus our backward force to get the net force. So that is mg sine theta minus mg mu cos theta. Now that we know our net force, we can find our acceleration. Mass times acceleration equals force, but let's make this the net force so we'll know how much it'll accelerate. Divide, actually what I did here, mass times acceleration equals our net force, divide by mass, and we get mg sine theta minus mg mu cos theta all over mass. The m's will cancel out. We can pull our g outside of the parentheses, and we end up with acceleration equals g times the quantity sine theta minus mu cos theta. This mu cos theta is only the frictional force, so if you just take g sine of theta, that will give you the acceleration if you had no friction. And I think maybe you could imagine that right here. If you have this block sliding down with no friction, you just take g sine theta to get acceleration. Mass times acceleration equals force, so we can multiply mass to that if we want. Next page. That was the formula for inclined plane. Now I'm going to do banked curve because it's almost identical. It just has a different backward force. Take a ball on a rope or a weight on a rope, swing the rope around your head. You're going to have a certain amount of centrifugal force pulling out. Mass times acceleration equals force. Acceleration equals v squared over r. So mass times v squared over r equals the force. If you had a tensile or tension scale on that rope to measure how much tension or force was on that rope, then you would use this formula right here. In reality, I'll just throw this in here for a little bit extra. You're going to have g from gravity pushing everything down, so things will not swing out perfectly horizontal if you're under the influence of gravity. This looks like a ride at an amusement park where people sit in those swings and they get spun around. So here's how we measure that force according to some basic trig. If we just take cosine of 0, so we're swinging this thing around here, just say in outer space or something, so that ball is swinging around at 0 degrees or horizontal, that's 100% force. So if we had a scale on that rope, which I showed here is like these springs, the springs will be stretched way out because we'll have full force. Now let's stand at the bottom of a cone, and that cone will have, say, a 45-degree angle. As we swing this ball over our heads, it's hitting up against this 45-degree angle, so it's taking out some of our force. So the springs here are a little closer together. So what this means is our force will be divided. Some of the force will want to go horizontal into the ramp. The rest of the force will want to climb up the ramp. Or I guess I should say the rest of the force will tend to make this ball or this mass climb up the ramp. The tension scale on our rope will measure that climbing force. We can also measure this climbing force by putting a scale right here perpendicular to the ramp, and then that ball will hit the scale there. Or if you don't want to use a ball as an example, you could also say this is a race car going around a banked curve. So if this curve is not banked very much and this car is going extremely fast, the person sitting in their seat is going to feel a pull to climb up that ramp. If the bank on that curve perfectly matches the car's velocity, then this person will not feel an upward climbing force on them, causing them to lean over in their seat. Instead, they're just going to feel a downward force directly from their body down into the seat and into the chassis of the car. And then if we have 90 degrees, so if we're swinging this ball at the bottom of a cylinder and that ball is hitting up against this wall right here that's vertical, then all of our force will be going directly into the wall perpendicular, and we won't have any force making this ball want to climb, so the scale on our rope will register as 0. So cosine of 90 degrees equals 0 force, so there will be no climbing force. I showed the forward box earlier, which gave us the information as in regard to how much forward force there was. This is the backward box. My lines aren't exactly parallel. So mg pulls everything down right here. We don't have to worry about friction because in this case, we're just calculating the backward force from centrifugal force. As I just showed, mass times v squared over r gives us the full force right here at horizontal. So let's find the adjacent leg. That'll just be cos of theta equals backward force over the hypotenuse, which is mv squared over r. So cos theta equals that. That means mv squared over r times cos theta equals your backward force. This part at the bottom here, I was going to just show that you could get acceleration also, but I'm not going to open that can of worms. So I showed forward force and backward force. On the next page, I'm going to show how to put those together. So say we have a vehicle that we know is going to be going around a curve. Maybe it's a country highway or something, or a normal highway, whatever. Or maybe we have a train going around a curve on some train tracks, and we need to know how much to bank those train tracks. And we know how fast that train is going to be going around the tracks, or I guess you could say a roller coaster also. So let's set our forward force equal to the backward force. Mg sine of theta will equal m times v squared over r cos theta. I'll do several moves at once here. Take cos theta, bring it over here, put it under sine theta. Then we'll have sine theta over cos theta. Mass on each side will cancel out. Take your g on this side, bring it under here, and put it underneath the v squared. Thus, we'll have sine theta over cos theta equals v squared over rg. Sine theta over cos theta is tan theta. So tan theta will equal v squared over rg. Thus, if you know the velocity of the vehicle, the radius of your circle, or in gravity, of course, will stay the same. And then you can find out what angle you need to bank your curve. On the next page, I'll put it all together. So the next page could look very overwhelming and just swamp you with detail. But since I just covered every detail in this video, this just puts it all together. Here we go. We have our forward force, which is mg sine theta. We have our backward force, which could come from two things. It could come from centrifugal force, mv squared over r cos theta, or it could come from friction, mg mu cos theta. Mg is pulling down. You got your normal force pushing up, which is mg cos theta. You could use the 90-degree rule that I explained earlier. You take your mg, multiply it by mu, then you go up, turn 90 degrees so it's horizontal, and you've got mg mu right here for the horizontal line or horizontal vector. But that 90-degree rule also works for your normal force. Normal force is mg cos theta. Multiply that by mu. That means you go up, turn 90 degrees. Now you have mg mu cos theta as your backward force, or the frictional force resisting the block sliding down. Notice I made the angle of theta equal to 30 degrees, and 30 degrees is closer to horizontal instead of vertical. That means we're going to have a very small forward force because the angle is not very steep, and we're going to have a large backward force, which means we're going to have a lot of friction holding it back. Or if this is a car going around a curve, that means we're going to have more centrifugal force pulling it back. And that's it.